Welcome back to real time digital signal processing course. So, we are discussing about discrete cosine transform in image processing. So, we will continue in today's class also DCT basically. So, in the last class we discussed about discrete cosine transform, where it is being used. We know that it is in JPEG compression. So, today we will continue with some of the properties what we are discussing about JPEG. So, here we will see the JPEG modes. So, that is the first one is we can have sequential mode, that is each image is encoded in a single left to right, top to bottom scan. So, this technique we have been discussing so far is an example of such a mode, also referred to as the baseline sequential mode, and it supports only 8-bit images as opposed to 12-bit images as we have discussed it earlier. Coming to the second mode, so we will see that it is lossless mode, that is truly lossless what we call it. What do you mean by that? So, we will be doing the predictive coding mechanism opposed to the baseline mechanism, which is based on DCT and quantization, that is source of the loss. So, here the simple block diagram of the technique is what it is shown in this. So, what we have is this is the image what we have it. So, we will find the predictive difference, so which is shown in this diagram. Then we will do the Huffman encoder, then we will be calling this as the lossless coding. So, as you can see in this figure, there are 7 predictive coding techniques which is going to be used. Here it is going to be unknown parameter in the P1 and the surrounding images pixels what we call it, which are 0, 0 and 1. In this case in the P2 mode it is going to be 1, 0, 0 and so on what we will be using it. As you will be seeing in the P5 we have 1 minus half and then half. Same way with P7 we have half, 0 and then half. So, we will see predictive coding how it is going to be used. Only we are going to consider the difference in this case. So, that is for each pixel a predictor, that is what we shown, one of the 7 which is listed in the table here is possible. So, that is used best predicts the value contained in the pixel as a combination of up to 3 neighboring pixels, as you are seeing it. This is the pixel. So, it can be A, C, B, R, these 3. So, the predictor with respect to that, if it is in the P1 only A what you will be selecting, it P2 B and P3 C, and then the other combinations what you can see the thing up to P4 to P7 with respect to A, B and then C. What we say is the difference between the predicted value and the actual value, that is x, contained in the pixel is used as the predictive difference to represent the pixel, instead of directly sending the value of that pixel. So, we will be computing predict the difference and then what it belongs to, so that number of bits are going to be less to represent them. The predictor along with the predictive difference are encoded as the pixels content. So, the series of pixel values are encoded using, as in the previous slide it depicted, using the Huffman coding. So, one has to take care of it, that is what is this nodes. The very first pixel in location 0, 0 will always use itself, and pixels at the first row always use P1, that is a pixel in row they will use P1, and pixel at the first column always in this use P2 technique. Okay. And then the best, that is what of the 7 predictions is always chosen for any of the pixel in this portion. So, here it is selected as 5 by 5 pixel what it is shown, but usually we will take 8 by 8 pixel as the sample. So, then how we are going to continue with the progressive mode. So, from the previous one predictive. So, we will see progressive how it is going to go. So, it allows a coarse conversion of an image to be transmitted at a low rate, which is then progressively improved over subsequent transmissions. So, as you will be seeing, spectral selection, send DC component and first few AC coefficients first, and then gradually some more AC coefficients what you will be selecting it. So, what is it? So, you will be seeing that in the 8 by 8. So, these are your red depicts your DC coefficients. So, first scan you will be sending all the DC coefficients. In the second scan what you will be seeing it. So, you will send some few AC coefficients. Like that you can send some more AC coefficients which are dominant, as you can see the thing. The last one is yellow, that is nth scan you will be sending these coefficients. This is how in the progressive mode you will be sending the coefficients. So, as you can see that in the progressive mode, successive approximation, all the DCT components are sent few bits at a time. For example, send n1 what it says is 4. So, you are seeing that these are the 4 pixels which are sent. Okay. Bit starting with MSB of all pixels in the first scan. The next n2 say, in this case only one bit what it will be sent here, that is the complete length of it. So, you will be seeing that this 4 bits, that whatever the length of it is going to be our first scan, and then the second scan what you are seeing it here, and then bits of all pixels in the second scan, and then so on what you will be doing it. So, you are seeing that till the end, okay, that is LSB bit. So, that is 1 pixel what for the rest of the thing what you will be sending it. Last one is, that is in this case it becomes 5th scan which you will be transmitting yellow, and then this is what you have ordered the pixels in the zigzag wise basically on this axis. So, the other mode is the hierarchical mode what you have to incorporate. So, this is used primarily to support multiple resolutions of the same image, which can be chosen from depending on the target's capabilities. So, the figure shows here a description of how a 3-level hierarchical encoder or decoder is going to work. So, what is it? So, you have I as the image input here. So, you have a 4 by 4, you call it as I4, then do the encoding of it, and then you will call it as L4 basically, and then you will be at the decoder end, that is you will be doing the decode and do the conversion to 4 by 4, and then output will be I-4 what you will be getting it. So, the same thing encoded at the encoding side also, you can decode and then convert it into 2 by 2. So, you will be seeing that the next 2 by 2 whatever image thing what you have taken, you call it as I2, then find the difference between these two, and then you will be encoding this value and then calling it as L2, and you will be transmitting it. So, the same thing, the next level is you are passing this encoder to decode, and then you will be doing the addition of the thing from whatever 2 by 2 what you have it, and then you will call it as the 2 by 2, and this will be passed on to the third level. So, which will be subtracted with respect to the original I, and then do this encode and call it as L alone. And again at the decoding place, you are doing the decode of these 3 level whatever encoded message. So, we got I4 dash. Now, the same thing what you will be taking it and then doing it as 2 by 2, then you will be adding with whatever you are getting from L2, and that you call it as I2 dash. The same thing will proceed to the next stage, that is 2 by 2, and then whatever decoded at this last stage is going to be added, and then you will be calling it as I dash. Okay. So, where this JPEG common applications lie? So, one of the application is the JPEG format what we have it, and in MPEG 1, that is this is the joint this thing group what you have it. This is MPEG is the moving average what you have 1 and then 2, and then MP3 is the audio player, and even in the advanced audio coding, and then in WMA most of them use our DCT method for compression. So, that is what is common in all these applications, what you have the DCT coming into the thing. So, now we will see a little bit on one dimensional DCT, how does it look like. So, we say n be a positive integer, the one dimensional DCT of order n is defined by an n by n matrix. C will be using A and C interchangeably. So, wherever C matrix, in some of the applications we may call it as A matrix. So, whose entries are given by, that is C I comma j is given by A I into cos I of 2 j plus 1 into pi divided by 2 n. What is the advantage of orthogonality? We will see the thing. If C is orthogonal, then we say that C transpose C is going to be identity matrix I. That implies that when you take a inverse of C, which is equivalent to C transpose itself. So, this makes solving the matrix equation easy, that is shown here, that is y is C into x into C transpose for x. Then what happens to C transpose y when I take C transpose of y and then C transpose on the right hand side also. Then it becomes C transpose C into x into C a transpose here, which is nothing but x into C transpose. If you multiply with C, okay, C transpose y into C is nothing but x into C transpose C, which becomes x. So, now you will be seeing that how y and x can be computed interchangeably, basically that if our matrix is orthogonal. So, x will be what is it, C transpose y into C, whereas original y is nothing but C x into C transpose. So, this helps in computation, that is both synthesis and analysis equation becomes easy for us to do the computation. Now, we will see for the discrete cosine transform, that is we have taken here n length basically. So, one basic characteristic is it is real orthogonal matrix. So, what is it, which is given by C is equal to root 2 by n into the all the first columns are 1 by root 2. So, the next one is cos pi by 2 n and then cos 3 pi by 2 n and so on. So, the last one entry will be cos 2 n minus 1 into pi divided by 2 n. And in the last row what we have cos n minus 1 into pi by 2 pi and so on, and the last entry will be n by n entry is cos n minus 1 into 2 n minus 1 into pi divided by 2 n. Now, we will see either C inverse as C transpose, how does it look like, that is root 2 by n, and we know that row becomes column in this case, and you will be seeing cos 2 pi by n, and then this row is becoming this column, and you will be seeing this last column entries cos of n minus 1 into pi by 2 n and so on, and then this is the last n by nth entry is the same as the original. Okay. So, how we are going to do the classification of our DCT algorithm? So, either we can do direct 2D method, fine. This 2D transforms what we call it as both DCT and IDCT to be applied directly on the n by n input data items, or we can go with row column method. That is, the 2D transform can be carried out with 2 passes of 1D transforms. So, we will be applying the separability property of 2D DCT and IDCT allows us to transform apply in this 1D fashion, that is one dimension row then on the other column. So, this requires what we say 2n instances of n point 1D DCT. So, to implement an n by n 2D DCT, that is one of the advantage of using it. And then what we call it is this computation is in place. So, what do I mean by in place is, so whatever the original your matrix what it has it, so same thing can be replaced with the new data, so that I need not have to have more storage for this computation, and it is much faster also, we will see in a while. So, now how we are going to do the row column decomposition. So, we said that separable row column decomposition what we will be using it. So, in the matrix form what it is given as z is equal to a x into a transpose what we have it, and then a k of n is nothing but root 2 by n into c of k. N is the order what we will be taking it, and then these are the cos 2 pi into 2n plus 1 into k divided by 4n. So, these are the coefficients what we have it, k and n will be varying between 0 to n minus 1, and we know the first coefficient c of 0 is root 1 by 2, and then the other coefficients k is equal to 1 to n minus 1, that is what it says. For k is not equal to 0, c of k coefficient is going to be 1. As you can see in the previous this thing, you will be seeing that this is root 2 by n what we have taken the thing. So, this is 1 by root 2. So, you will be seeing that the first c 0 is 1 by root 2 basically. So, which we can take it as 1 by root 2, and then rest of them we can assume it as 1. Then what happens to our equation? So, x is the input or 1D DCT unit. So, what we are going to compute here, y is equal to the first stage of the thing a into x. Then we will be doing the transpose the memory of y. So, why we have to do the transpose? So, you will be seeing that this is my transpose of y, here it is c what it has been done, here a into x what we will be transposing. Then I will do the 1D DCT, same unit I can apply 1D DCT unit, then I will be getting y into a transpose. So, that is my z what it is shown here. So, this is how we do the row column decomposition and then computation. Now, why we have to use this? Okay. So, carry out the computation as a full matrix vector multiplications. We know that 1D transform requires n into n multiplications, which is nothing but order of n squared multiplications, and then n into n minus 1 additions what we needed. So, this also order of n squared, whereas our 2D transform requires, as we know that all is length n which is going to be order of n to the power of 4 and then multiplications, and this one order of n to the power of 4, that is n into n minus 1 additions what we needed if we are using direct 2D transform. So, although requiring most number of operations, this method is very regular and more suitable for vector processors or deeply pipelined architecture what we have discussed for high processor execute or processor engine basically utilization. So, what is it? So, we can have 1D fast algorithms, we can just like our FFT we can configure our DCT also for the fast algorithm, which brings down to order of n log n instead of order of n squared what we can have computation. Whereas a 2D fast algorithm we can incorporate it in order of n into n log n ways, that is order of n squared log n what we will be getting directly if we are doing the 2D algorithm. So, one of the applications I will be showing that how this can be incorporated later. So, now we will see why we need the compression. We have been discussed in the last class also. So, there are different ways of doing the compression. So, we know that is a method that reduces amount of memory it takes to store in image. So, we discussed in the last class, so with 3 millisecond data how much video we have to store it. So, how we can reduce it. So, that DCT matrix is based on our visual system for the purpose of image compression, and this means we can delete the least significant values without our eyes noticing the difference. There are different ways of doing the compression. So, the first one we have discussed, we will just go for one more time to see the thing. So, what is it? We have found this matrix, that is Y is C transpose whole transpose what we wanted, and we say in this case this is the most important part in our image what it is required, and these are semi important and these are the least important values what we are interested in. So, using the DCT, the entries in Y will be organized based on the human visual system. The most important values to our eyes will be placed in the upper left corner of the matrix, and the least important values will be mostly in the lower right corner of the matrix as you are seeing it here. So, the next one, to show that what are the DCT coefficients, how it is ordered. So, you will be seeing that the first corner you will have the DC in terms of frequencies, DC component is here, and rest of the frequencies, that is low frequencies which are present in the this domain. Same as our previous one, we have the medium frequencies and these are the high frequencies. Most of us know that high frequencies is a noise, so that we can eliminate that. And then when we are looking at some of the edges what we are going to want to put it in the frequency domain, that is in the DCT coefficients. So, we will have the DCT and the vertical edges are represented in the horizontal coefficients, whereas the horizontal edges values are represented as our column wise in this, and all these are high frequencies what we will be representing it. So, coming to the image compression, so you will be seeing that it is 8 by 8 pixels. So, this is the grayscale what we have taken the thing, that is some of them are white, some of them are black, and then some of them are grey. So, this is how the pixels can be taken, or one of the best way of doing it is take a checkerboard which has both white and black components only, and then see how the compression is going to look like. And then we have taken an image here, all of you know that this is an input image Lena. So, which is there in the MATLAB, you can choose this, or from anywhere you can download different images and then you can represent. So, we will see the compression how it is going to have it. The first one is we can do a grayscale example what it is taken. So, the value what we will be representing is 0 to 255. So, 0 represents black and 255 represent white, and in between values will be different levels of gray what we will have it. So, as an x, what you will be seeing is these are the values what you will have it in the matrix. Okay. So, you will be seeing some of them are 214, 208, 198 and other things. The first one is 63. So, now we will have we will do the so 2D DCT of matrix, what we are going to do it. So, numbers are coefficients of a polynomial what we will take it, and this is after doing the 2D DCT for this x value we will be getting y. Okay. So, these are the values what it is represented. So, we can see that this is DC minus 304, which is what we call it as 255 white, and then you will be seeing that they will be having different values. Approximately this is minus 327 and 260 what you will be seeing somewhere here. Okay. So, some of them are that is represented as black, and then you will be seeing rest of the thing, and then you are seeing that some of them have very less values. So, what is it? I can put a threshold. So, that is above that I will be making them zeros, or below them I will be making zeros, and above threshold I will be making them whatever they have it. So, what is the threshold? You can put the thing here, as you can see that the values less than arbitrarily here it is chosen. Okay. As you can see here, I have a 12 here, 30. Okay. So, some of them are getting eliminated. One way of doing the thing is I can put a threshold saying that above any value 10 or below that what I am going to make them zeros. I can do that way, or one corner of it what I can do it, because these are going to be zeros. So, what you have selected is from here you have made them zeros, basically all of the lower side of the matrix. Okay. So, this is one way of selecting. Rest of the what we say, we are going to keep the coefficient as it is, that is cut the least significant components. That is what it is done. That is we save a little over half the original memory by doing it. So, this is one way of doing our compression. So, in the next class we will see other ways, that is we will use the quantization matrix. So, to say that we will be dividing by that quantization matrix, and then we will discuss that how it is done, and then we will take the demo of the DCT also. So, thank you, and then happy listening. We will meet in the next class.